Alright, so you guys, we're going to go ahead and do 4-1, 4-2 today instead of Tuesday, then review Tuesday, take the test Thursday. This is how I want to start out 4.1, just see if you guys can state the vertex of that graph. College algebra or 302.
Minus opposite of b minus or over 2.
Yeah, there's two ways to do it. One way is, this is a parabola, it's got an x squared, it's positive, we know it goes like that. Right, so its vertex is going to be right there. A lot of people remember the x is just the opposite of b over 2a. That's how you find the x of the vertex. So,
you put the x into the equation before?
So here, if I take the opposite of b, I take the opposite of negative 12 and put it over 2 times 2. When I get 12 over 4, I get 3. The x coordinate of the vertex is 3. And then if we plug that back in, we do f of 3, that finds the vertex. 2 times 3 squared would be 18. Minus 12 times 3 is 36, plus 13. Right? And you know you did this right. You got the right x because this number should always be half of this number. You did it right. And let's see. 18 plus 13 is 31, minus 36 is negative 5. So that vertex is at 3, negative 5. Right, the other way we could have done is completing the square, put it in vertex form. Right, but I was hoping somebody would say this, the opposite of b over 2a. So I always wonder, I wonder if people ever wonder, where does that come from?
Yeah.
You never do?
Smell it.
I do.
It's not good.
Not really.
Here's what we're going to do, Terry. 4.1 is extrema on an interval. Extrema are just places where a graph changes direction. All right, so it says, here's definition. It says f of c is the minimum of f on some interval if f of c is less than all the other functions for all the x's or all the other y's, which should make sense. If you're in a certain area and the graph goes to a lowest point, that's a minimum. And this is saying it's a maximum if f of c is greater than all the other f of x's, or this is basically saying y's. If the y at the value for c of x, and x is c, if that's greater than all the other y's, then you have a maximum. Okay, so extrema are minimums and maximums. So the minimum and maximum of a function on an interval are the extreme values, or extrema. The singular form of extrema is extremum. Of the function on an interval. Minimum and maximum of a function on an interval are also called the absolute minimum, maximum, excuse me, or the global minimum, global maximum on an interval. And then they give us a couple theorems here. I just copied these theorems out of the book. So the extreme value theorem, f is continuous on a closed interval a to b, including a and b, then f has both a minimum and a maximum on the interval. If you think about it, if you have a graph, what this is saying here is if we have a graph, right, and say the graph does something like this. Okay, but we only look at that graph from here to here. Then that graph right here has a minimum at this lowest point, and over here it has a maximum. If it's on a closed interval, it always has to have a minimum or maximum. Okay, if we only looked at it from, or maybe the graph went up more like this and it came back down to here, then the maximum's here. But on a closed interval, there has to be some point where it reaches its highest point and some lowest point. And then the big one here says relative extrema occur only at critical numbers. If f has a relative minimum or relative maximum at x equals c, then c is a critical number. And it's important to know critical numbers occur where the first derivative is 0 or undefined.
Where's that?
Think about this. We had this parabola here. If I drew a tangent line at the vertex, right, it's a horizontal line. That tells us at that point right there, f prime of x equals 0. So that x is a critical number because it changed direction, and the critical number occurred where the derivative was 0. All right, so you go over these theorems. And then I sort of, I don't know, abbreviated this or summed it up. I like to think extrema are relative maximums, relative minimums, points where the graph changes direction. That's what those theorems are saying. They only occur at critical numbers, and critical numbers are places where the first derivative is 0 or undefined. And on a closed interval, extrema are absolute, meaning there's one maximum and one minimum.
There's no absolute minimums or maximums if it's continuous?
No, because it
goes to infinity and like or negative continuous.
Yeah. So if I grab just that function, we found the vertex. All right, what was it? It was 12? No, it was 2x squared, right?
Yeah.
2x squared minus 12x plus 13. Oops. So 2x squared minus 12x plus 13. If I graph that, whoops, kind of weird. We'll go back to Zoom 6. Let's do a standard graph. If you look at that has actually an absolute minimum because the graph never goes lower than that.
But there's no absolute maximum.
There's no absolute maximum because the graph keeps going up forever. Right now, if we do this on a closed interval, maybe we just look at it from, oh, say 0 to 5. Okay, now on this closed interval, there's an absolute maximum right there. Or if we're only looking at it for x's from 0 to 5, it has a highest point and it has a lowest point. Right? But if we let it keep going on forever, it never has a highest point. It keeps going. Any graph that changes direction. Let's say we had a graph that does, oh, I sketch a graph that does something like this. If that graph has no absolute minimum, no absolute maximum, right? Because it keeps going down forever, it keeps going up forever. But it has a relative maximum here and a relative minimum here. So this relative area, or they say another thing, this global area, that's the highest it goes. This is the lowest it goes in this general area. So that's a relative minimum, that's a relative maximum.
What was the word you used?
They used global.
Oh, global.
Let's see.
Oh, instead of absolute.
Yeah, different books use different words. They use global minimum, global maximum. That's the same thing as saying relative minimum, relative maximum. Or actually, I take that back. Those are the same thing as absolute. So they're using global because this is saying here on an interval. Right? So if it's on an interval, if we restrict where we're looking, there's always a highest and a lowest point in that thing. So they're saying global on that closed interval. But if we're just looking at it forever, wherever it changes direction, that's an extreme. Okay, those only occur where the first derivative is 0 or undefined.
The extreme or the relative maximum.
Right. And sometimes a relative minimum is a absolute.
Yeah.
Right? In the case of this, that's a relative minimum and an absolute minimum, because even if we let the x's go forever, the graph always goes up. All right, then in the book they give you some guidelines here for finding extrema on a closed interval. They say find the critical numbers. Take critical numbers where the first derivative is 0 or undefined. Evaluate the critical numbers in between A and B. Evaluate the endpoints of A and B. The smallest one's the minimum, the biggest one's the maximum. And so if it's on a closed interval, we've got to check the endpoints of our interval too. Let me see what we missed.
There's an endpoint formula, right?
A what formula?
An endpoint formula? Am I wrong with that?
What do you mean endpoint?
It says evaluate at each endpoint, so it's the same. So endpoint is just the A and B?
Yeah.
That's the interval given.
No?
Yeah, if they give you an interval. But it's like, see, I got that here, but then I just say here, find all the extrema of this function. So if it just says find the extrema, you're looking for places where the graph changes direction.
Where the first derivative is 0.
So extrema, you can think if you want a working definition or just a simple definition, I guess, are places where a graph changes direction. Yeah, for a graph to change direction, this would do something like that. A tangent line would have to be horizontal. So that's where the first derivative is 0. So we would take the first derivative. So f prime of x will equal what? 3x squared minus 5x plus 1. 2 times 5 is 10. 3x squared minus 10x plus 3. So we want to know where does that equal 0. We take that, set it equal to 0. On a factor, we could do that. Factor, we do 3 times 3 is 9. Look for two numbers we can multiply to get 9 and add to get negative 10.
Now, could you actually do the that negative b over 2a in that situation? Or would that have any meaning in that particular function?
Only if the original function is quadratic, with the opposite of b over 2a would. If the first derivative is quadratic, no.
So what is the value then of that in this function, I guess? Would it have any representation on the graph?
The opposite of b over 2a only works for quadratics.
Okay.
And maybe if we go back to this, maybe I'll show you. Let's say our function was any parabola. It was ax squared plus bx plus c. All right, so we can have any number for a, b, and c.
Right.
What would be the first derivative of that function?
2ax plus b.
Plus b,
Yeah.
right? If we took that and set it equal to 0, what would we get? Solve for x. We subtract b from both sides. Get 2ax equals the opposite of b. Divide by 2a, and x is the opposite of b over 2a. That's why it works with quadratics, but not with others.
Okay.
All right, so this was a cubed, so we want to take the first derivative, set it equal to 0. And I'm thinking two numbers we can multiply to get 9 and add to get negative 10 would be negative 9, negative 1. So I'll take this 3x squared, I'll replace the negative 10x with negative 9x minus 1x plus 3. All right, so I haven't changed the value, I still have a negative 10x there. But then I can split this down the middle, take a 3x out of both of those, be left with x minus 3. Over here I could take out a negative 1, be left with x minus 3. So I've got x minus 3 in both terms. I'll factor that out, get x minus 3 times. I'm left with 3x minus 1. So critical numbers are 1/3 and 3. Right, those are places where the graph probably changes direction. Right, if the first derivative is 0, we've got a horizontal tangent line. So one of them, think about it too, when you've got an x cubed, the graph should change direction twice. Right? The graph normally changes direction one fewer time than the highest power on x, or it can change direction at most that many times, and it has that many zeros. So this thing changes direction twice, so it leads me to believe one of these gives us a minimum, one gives us a maximum. So what they're saying here is to figure out, we go back in here and plug them into here.
Wait, I think you just said it changes directions the same amount of times as the x to the third.
No, it has that many zeros.
Oh, that many zeros, which is how many times it crosses the x-axis.
Yeah. So the highest power on x tells you how many times it can cross the x-axis. Subtract 1 from the power, that tells you the most times it can change direction. So let's see, if we go in here and find f of, I'll do f of 3 first. If we plug 3 in here, I need to leave myself one more room. Didn't write those together, did I? I moved it down here. So if we plug 3 in there, we get 3 cubed. 27 minus 3 squared is 9 times 5 is 45. Plus 3 times 3 is 9, plus 6. Let's see, 15, negative 30, is that negative 3? And so on this graph, we've got a point at 3, negative 3. If we plug 1/3 in there, I'll get 1/3 cubed is a 27. This is going to be harder to do without a calculator. 1/3 squared is a ninth, so we get 5/9. That won't be too bad. Plus 3 times a third is 1 plus 6. So let's see, 1 plus 6 is 7. If I multiply this top and bottom by 3, I get 15 over 27. 1 minus 15 is negative 14. Over 27. So if I borrow 1 from the 7, I get 6, and then 27 over 27 minus 13 over 14 over 27 is 13 over 27. So when x is 1/3, the y is 6 and 13/27. So which of those is the relative maximum?
The second one?
The 6, yeah.
The one with the bigger y, right? This is a relative max. And this one's a relative min. Another thing we could have done too, if the factoring, if we didn't want to factor it, we could use the quadratic formula from here. Right, from here I can take the opposite of b, do plus or minus the square root of b squared, that'd be 100. Minus 4 times 3 would be 12, times 3 would be 36, so 100 minus 36. Over 2 times a, 2 times 3 would be 6. So I get 10 plus or minus, that'd be the square root of 64, which is 8 over 6. 10 plus 8 is 18, divided by 6 is 3. 10 minus 8 is 2, divided by 6 would be 2 over 6, or 1/3. So we get the same axis. So if you don't have to factor it. All we want to do is figure out what x's make that equal 0. Sometimes factoring is easier. Sometimes people really good at the quadratic formula, they go with the quadratic formula. Now, you guys, when it says extrema, that's on an open interval. But what if this would have been closed, a closed interval here, and maybe we said find the absolutes, and we said just do it from, oh, let's say 0 to 5. Right, when you make it a closed interval, maybe let's just do this on another slide. Here, let's say, okay, what if this said find the absolute extreme?
Isn't it the same? You just have to figure out which one's the...
Yeah, we already figured out our critical numbers, right? They were 3 and 1/3. Right, we figured out when x was 3, what was y? Negative 3? When x is 1/3, y was 6 and 13/27. Now we have to add in, we have to check the endpoints. So we got to put 0 in for x. If I put 0 in for x, I get 6. And then I got to put 5 in for x. If I put 5 in there, f of 5 is going to be 125 minus 8. 5 squared is 25 times 5, that'd be 125. Plus 3 times 5 is 15, plus 6, that's going to be 21. All right, so when it's on a closed interval, you have absolute maximums and minimums. So now the 3, negative 3 is still our absolute minimum. Or it's still a minimum, but it's no longer just a relative minimum, it's the absolute minimum on this interval. And then the 521 is the absolute maximum.
Okay, so you're saying you find all of those things then?
Right. The only difference, and maybe looking at the graph too, well, is when it's on a closed interval, there's one absolute maximum, one absolute minimum. Unless 2 points are the highest, then there's 2. All right, if I came in here and I graphed x cubed minus 5x squared plus 3x plus 6. All right, if I just did zoom 6. So we found earlier, these are the extrema here, or the relative maximums and minimums. The calculator finds those. I can go into calculate. Number 4 finds a maximum. You just move the cursor, there's my cursor, make sure it's to the left of that highest point, hit enter. Then move the cursor to the right until you get past it. Now it's going down, hit enter. Ignore where it says in gas, hit it again. And 0.333, that's 1/3. And the 6.481, I bet that's 6 and 13/27. And then to find the minimum, you can go into calculate. Minimum is number 3. Okay. Hit the cursor to the left of the lowest point, hit enter, move it to the right, hit enter again, ignore the gas, hit enter again. Right, there's our minimum. There's minor flaw in the calculator, 2.99999. It's really 3, negative 3. So maybe I'll move that back here. We graph this here. So extreme are places where it changes direction, or they're relative minimums, relative maximums. All right, obviously this graph goes lower than here. It keeps going lower, so it has no absolute minimum. It goes higher than this point. It keeps going up. It has no absolute maximum. But in the second example here, if we restrict it to just look at the window from 0 to 5, and we graph it again, right? This is still the lowest it ever goes, but then it goes off the screen. We gotta change the window. We gotta at least go to 21. Huh?
But it still has a relative maximum of 1/3, right?
Well, once you make it a closed interval, you call it an absolute. Are you
The
saying?
absolute max is 5, so there's a relative max.
Yeah, there's a relative minimum here if you want. Yeah. But whenever they ask you to find it on a closed interval, you want to find the absolute minimum and the absolute maximum. Right, so that changes now, where we can say absolutely. From 0 to 5, it never goes lower than this, and it never goes higher than this.